Hi everyone, I'm Robin Williams in the UK. I'm a applied statistician by trade. I did my PhD in statistical methods for weather forecasting, and I now work in industry as a sports statistician, producing statistical models for predicting the outcome of various sporting events, major sports. Um, I'm fully blind and make use of speech, braille, and sound as part of my workflow. What I'm going to demonstrate today is an R package that was developed between myself and a friend and colleague of mine whilst I was doing my PhD. My friend said to me, "Have you ever considered trying to turn data into sound?" I think when he saw me struggling to interpret some graphical information, I said, no, not really. And we set about developing this package. It's quite a small package, and I would like to expand it, but it has its uses, and it's a regular part of my workflow. Um, so a very quick bit of background on how it works. The main function, which is called Sonify, as is the package also called Sonify, it can convert two-dimensional plots into a soundscape. How it does this is it interpolates between points on the plot using splines or some other local fitting technique. There are a few options. And it then uses a Fourier transform to produce a sound wave, and the pitch of the wave indicates the height of the plot or data points in the y direction. And if you're able to hear this in stereo, you will hear the soundscape pan from left to right as you move along the x-axis. You can also add tick marks, which I'll demonstrate. Plots that we produce, visual plots, typically have tick marks at regular intervals on the x-axis. So we have the functionality to be able to reproduce those. And you can also overlay some white noise if the graph that you're sonifying falls within a certain interval. And I'll try to demonstrate some of the use cases of that as well. So I just have a few examples here of some very kind of high level overviews of how we could use it. And I will ensure that the code to reproduce these examples is available as well, so you can work through them in your own time. Just for the sake of completeness, I'm running this demo in VS Code, using the VS Code integrated terminal that's running an R process. And I've already run a few lines of code to set things up. I've loaded the Sonify package, which is available on CRAN, which is the main repository for all the R packages. So the first function that I thought I would demo is just a simple sine wave. So with my code here, I've generated a sequence of x values from -pi to pi in some very small intervals. And then I've created a second vector, which is just the sine of those x values. And so we should be able to hear the periodic nature of the sine wave. So it's 0 at -pi, it's 0 at 0 and 0 at pi, and then it peaks and maximizes and minimizes at plus or minus 1 in the y direction. So if I just play the very simple example, so for those who can't see, the line of code I'm running to run this soundscape now is just Sonify brackets XX comma YY and just one additional argument to specify the media player that I want to play the soundscape in. So here we go. So that's just a very basic sine wave. As I mentioned a minute ago, we have the functionality to add ticks at any points of your choosing on the x-axis. So here I've added them at every pi over 2. So minus pi over 2, 0, pi over 2, and pi. And the sine function has either a minima or a maxima at all of those values. So hopefully we can hear the ticks now. So you didn't hear the ones at the very end because I think the equality condition is strict, but you would have heard the ones in the middle. I also mentioned earlier that we have the ability to add white noise if the plot falls within a certain interval. So here I've added the argument to my Sonify call of noise interval equals, and then the vector minus infinity to 0. So essentially, whenever the line that we're turning into sound falls below the x-axis, so negative in the y direction, we should hear some additional white noise. So you can hear there that the graph is negative for negative values of x, so between minus pi and 0, and then positive for positive x. If I was to extend the range of x beyond pi to say 2 pi, you would then hear more white noise as the function dips below 0 again. The calls to Sonify are quite customizable as well. So one argument that I use fairly often is if you're trying to listen to something in a bit more detail, you can specify the duration of the plot of the soundscape. So here, by default, the duration is 5 seconds. Here I've just done an example of the same soundscape as we previously heard, but with the duration extended to 10 seconds. Okay, cool. So those are that's the first example that I wanted to go through. Okay, so the next example I wanted to show of how I make use of this package is in hearing and therefore getting an idea of the shape of some probability distributions. So there are many probability distributions, and sometimes it's advantageous to know what they look like depending on the application that you're working in. And I think most sighted people would type normal distribution into Google and immediately have a graphic of the shape of the probability density function. So it can be useful here to kind of listen to how these things sound and therefore get a picture in one's mind of what these functions look like. So the first example, I'll just demonstrate the normal density plot. So here I've made some again, some X values. This time they can range from -5 to +5 in steps of 10 to the -4. So I'm now going to play a soundscape of those the normal density of those X values, the standard normal with mean 0, standard deviation 1, and I've added a tick mark at 0. So when I hear that, it becomes apparent that for those specified parameters, there isn't much or any real density at the left and rightmost parts of the plot, which is as we would expect. And then it kind of peaks quite sharply at 0, where I put the tick mark. So it's the classic bell curve. If I was to move the mean of this distribution to say 2, oh, I've got all capitals there for some reason. If I was to move the mean of this distribution to say 2, we will hear something different. So you can hear there that you've got more area on the left-hand side of the plot with no density, and that the peak is no longer at 0. The peak's, of course, at 2, where the mean is. Another example I cooked up is the exponential distribution. So this distribution has no support, no density for -x. So I've generated some more X values just between 0 and 5 this time. And we can listen to how the exponential distribution sounds. And the exponential distribution has a rate parameter. And so we can play around with that and see how the shape of the distribution changes as we change the rate parameter. So here's the distribution with the rate parameter of 0.5. So it essentially sounds like a exponential curve, as one might expect. If I change the rate parameter to 3, you can hear there that the gradient of the curve is much steeper, and we quickly reach a point at which we have no or minimal density much more quickly than in the previous example with the rate set to 0.5. So those are a couple of examples of how I make use of the package to get an idea of different probability distributions. There are some fun ones out there, so play around in your own time. So the third example I wanted to demonstrate is in how can we make use of this package to help us in some more applied work. So something that a statistician might typically do is to fit a model to some data. So you would have some input variables, and you might be predicting one or more response variables using some model. And the classical thing that people will be taught to do in their first or second year statistics course at university would be to check the validity of the model that they have fitted with some diagnostic plots. That's a bit trickier for us if we can't readily see the diagnostic plots. And this was really where the package idea was born. So here I've generated some synthetic data, and then I'm going to deliberately fit a model that's not specified properly. And then we're going to plot the residuals of that model against one of the input variables, and we'll be able to hear where uh, we'll be able to get an idea of how those residuals vary as a function of that input variable. And if you are then able to extrapolate that information, you could um, arrive at an idea of how the model could be improved. So I'll just run through this code. So we're going to simulate 10,000 data points. So I'm going to simulate some data that is quadratic in nature. So I have a variable x, which is going to be my input variable, and then I'm going to simulate my response variable y, which is a quadratic function of x with some white noise around it. And then I'm going to fit a model, which is just a linear model using the lm function in R, but I'm only going to specify the linear term, the first order term in X. So I'm not going to specify the quadratic term. So it's deliberately misspecified. So if I fit that model, and now what I'm going to do here is in R, there are functions that enable one to fit a line of best fit to a data point. So one that's quite often used is known as LOESS, LOESS, and LOESS essentially is a smoothing approximation to the data that's around it. So uh, yes, it will fit the line of best fit, but it's not restricted to be of a certain shape. So if your data is wiggly, your line will be wiggly. If your data is very linear, your line will be very linear. And what I have here is a wrapper function um, called audio lowest. So audio lowest makes the lowest call within it and then calls Sonify to convert the output of the lowest call into sound so we can hear the shape of the lowest line that's fitted. So for those that can't see the screen, my line of code that I'm about to run is audio lowest, and then specify my input variable, which is my x, and then the thing that we're going to fit to are the residuals of the model that I just misspecified deliberately above. I've added a tick at 0 and a noise interval of, again, -infinity to 0. So any negative values of the lowest line should be overlaid with white noise, and we can hear the shape of the residuals of that model as as X pans from left to right. Okay, so we know that the model was deliberately misspecified so as it didn't include the quadratic term in X. And therefore we know already that the residuals we would expect to follow a quadratic shape. But hopefully one could deduce that or something similar to it if you didn't know that by hearing that soundscape. And you might be able to think, okay, I'll go and I'll refit my model with um, a quadratic term included. Um, you can, if you want to experiment with the kind of range of residuals or the range of your lowest line, a handy thing to do is to play around with the specification of the noise interval. So in this line here, I've changed the noise interval to be between -infinity and -5 rather than -infinity and 0. So if we don't hear any white noise in this plot, then we know that the lowest line never passes below the value of y is -5. So if we listen again now, so from those two soundscapes, you could deduce that we heard some white noise, a small amount in the first plot, and no white noise in the second plot. So the minima of the lowest line that I'm sonifying is somewhere between 0 and -5. So this is a similar idea with a misspecified model. So I have the same x values as before, and now rather than fitting a quadratic, rather than simulating a quadratic function of x, I'm going to simulate a linear function of x plus a fast oscillating sine wave in x. So my y function, for those that can't see this, is kind of a plus bx plus c of sine of 5 times x. So the period of that thing is quite fast. So I'll run that and then fit my model where, again, I'm going to deliberately miss the sine function. And now I'm going to do the same thing. I'm going to play the lowest line of the residuals of that model as a function of x. Okay, and I think the only really useful thing to say about that is that you can hear where the sine wave is missing in the middle, where it kind of wiggles up and down quite fast. The other thing that's interesting to note is that shape should in theory persist throughout the range of x, because it's misspecified for all x. However, it doesn't. You would have heard the linear kind of increase at the beginning and the decrease at the end. And that is actually a symptom of a kind of shortcoming in the lowest function itself, where because I have much less data at my extremes, the lowest function doesn't do a particularly good job of fitting to the data that it has. If I was to play around with some parameters of the lowest function, might be able to improve that, but that's something that my sighted colleagues at work tell me they often see, is that you can't rely too much on lowest or similar functions at the extremes of your data, and I think that's just an example of that right there. The final call I have is just with a noise interval added here. So if we do that, so yeah, you can hear there that the lowest line is negative at the beginning and then kind of oscillates between positive and negative in the middle, which is where it's more reliable, and then dips below 0 again. And I have the code here for those who do have the vision to be able to see it, to plot that curve. Hopefully I've done this correctly. Sorry, that's the mistake I've made, is I've plotted the wrong thing. I need to plot this instead, and then we'll actually hear the right thing. Sorry to the video guys here. Let's do this again. And I'll fit the lowest. Okay, now I think the lowest line should represent that you can see visually should represent what we were hearing. Okay, perfect. So yeah, this is how I make the most use at the minute of the package in an applied sense. Some extensions I would like to make include, but aren't limited to, I need to find a way of being able to quantify the variation of the data in different regions of the graph. So sometimes you have a data set that's very kind of clustered together, some values of your X variable, and other regions of your scatter plot could be much more variable. So I need to come up with a way to be able to soundscape those. And the other thing that should be very doable, I just haven't done it yet, is to have some representation of the density of the data. So in this plot that we have on the screen now, there will be much more data in the middle than at the two ends. And it would be an obvious extension to have some representation of how of that as well. So just to conclude for now, I wouldn't claim this to be a full replacement for tactile graphics. I'm a big fan of tactile graphics, especially if you can get them in on a refreshable braille display in one of these multi-line displays. But for a kind of free, which everything in R is free, and quick overview of plots and distributions and so on, I think this is it's still a useful addition, and I'm still making heavy use of it almost 10 years after we first developed it. I am going to make the package available on GitHub, and people are more than welcome to make their own contributions as well to improve it, or reach out to me, and I'm more than happy to discuss people's ideas as to how it can be improved and developed further. But yeah, I hope that was of some use. Thank you very much for listening. I hope that was beneficial, and please feel free to reach out to me with any questions or ideas as to how you can use this package and make it better.